speaker's working. Let me make sure my speaker's working. Not on. Okay. And then everything else is on. So Daniel, you can hear me, right?
Yeah, but the camera classroom is facing the wrong way.
Yeah. Weird. Okay. Okay, I can fix that. Maybe. Distance learning, camera. There you go. Okay. That's pretty weird, huh? So somebody messed around with it.
Yeah.
Oh, it is.
Yeah, continue.
Continue, but it's pointing completely the wrong way, right?
That's what you love. This move for channel. That's what you.
That's up and down. Oh wait, no, it's got a long memory. Now it's just going directly down. I can see it up there, right? Wait, where is the camera? That's pointing the right way. Oh, it's pointing up, down, I mean, all right. All right, let me just rotate 180 degrees. Oops, wait. It's not exactly a perfect control here. All right, now you're looking at the back of the classroom. You should be happy with that. All right, it's got a delay. Yeah, I need to turn it 180 degrees.
Look this one. The initial one will be the other time. Look this one.
Huh?
The initial one is the first one. Yes, coming on.
Okay, okay, we're getting there.
Is it okay?
We have the technology.
Yeah. Okay.
Yeah, see, I'm not touching it. It's got a delay. All right, that's pretty good. Zoom it in. That's good. Anyway, you shouldn't.
Yeah.
This thing's a pain in the neck. It must be Bluetooth. All right, is that good enough?
Yeah.
All right, so what else? But they shouldn't, that's just you should see my slide though, right? All right, that's just something. All right, so anyway, so let's just get through this paper. All right, so anyway, all right, so these guys, oh, I didn't open up, let me hide this. Hide floating screen. Make that this thing. So if you look at this nano lubricants, some web page that was there before. Looks like going slow here. Huh? All right. Anyway, so nano lubricants, these are the 4 things that you can do, so rolling ball effect. So this is what this guy's claiming he's doing. He's making these little macromolecular. They're actually mega molecular. So it's like millions of molecular weight, like 10, 50 million molecular weight. And he's making it from a dendrimer. See, does he have a picture of it here? This thing. So he starts with this thing. It's got 3. And then this is a ring opening polymerization that's going to have 2 here and 1 sticking out, OH, and then 2 other OHs. And they condense with these OHs. So water comes off. I don't know, he does it anionically, so it isn't exactly that. Normally you'd have like an acid and the OHs would break off, you'd make like either water or HCl or something from it. So ends up with these ether linkages like an oxygen and carbons. So the carbons have that 3, like a tripod motion, right? In other words, they have 3 positions that they can spin around, like with the energy, and the oxygen is just free spinning because there's no side groups, right? So oxygen, so you can think of this as like a universal joint, and these things are like toggles, the 3 toggle. The carbon's like 3 toggle, trans gauche plus gauche minus, and then this thing's just spinning. So whenever you see an oxygen, then the thing stuck to it's like a propeller spinning around, yeah. And then when you see the carbons, it's like a tock, tock, tock thing. like 3 positions. So anyway, so this thing's, you can think of this thing as like all those positions, like doing that kind of thing, that kind of dance, and the whole thing is alive in that way, like KT's spinning the thing around. So you can go to like 1 generation, 2 generation, each time it's got 3 arms coming off, except sometimes it has just 1 arm. Because you can have these different connections showing up, like only one can react and he still has an OH 2 ways, 1, 3, 1, 4. So that's a linear connection. Or you can have both react, he gets a dendritic, like a 3-way split. That's his 3-way branch. Then there's a terminal in the end, it's just OH, right? So you can stick this into an NMR, get a pattern. I don't know if they have patterns in this one, but anyway, you get an NMR pattern with peaks and you identify the peaks. I think he gives it in his supplemental here. There's a lot of the stuff's in his supplemental, like in Nature papers, 2 pages or something. So this is the NMR. So you can identify those peaks as linear. There was just 1 R on it. Dendritic with two R's. So bonded twice. And then terminal, the hydroxyl terminal. And from the area under those peaks, you can figure out like the percent of each of the things. I'm going to 2 different supplementals here. If I can find the other one I was looking at, because the other one says, so he's published this. So one thing is like Nature is supposed to be like a new thing, like something new, but he's published this since 2009. See, and the details of it are kind of buried in the other papers, you know. So it's kind of a funny thing. So he ends up with this thing. So he ends up with percent, like the relative abundance from that NMR pattern of the linears, 2 kinds of linears, 1, 3, 1, 4. He shows them up here in the dendritic and the terminal. Then he gets this thing, degree of branching. Well, if you look up like Google degree of branching for these kind of dendrimers, there's like different definitions of it, right? It seems like it's kind of a free for all. So you'd say if you have 25% dendritic, 3-arm branches in it, you'd say it's 25% degree of branching. That's what I would say. That's not what he says. He says it's, and also, if you look at the percent of dendritic, well, here they're all the same, but the percent dendritic goes up and down, like in this different, in his samples, you know. So anyway, but he always ends up with this 58% degree of branching. So this whole thing is a little mystical to me. So where does this number come from? Like you can try to guess, and no one actually says. Well, people say, but they all say a different thing, different equation for it. Anyway, I thought, well, if you add up the dendritic and terminal, the 25 and 32, you get 56, and you kind of get 57 and 58. And that's the only way I can see that you can get those numbers that he's reporting, you know, from these numbers. So somehow he's saying that branch is a terminal group. Like when they reach the end, and then it's just hydroxyls on the outside. So all these, the hydroxyls are going to bond. So the more, he actually wants to have these linears inside his structure so that it can suck water into the ball. He's going to put this into your knee joint, and it's got to have like it's got to be like a soaked, wet ball that's going to lubricate your knee joint in the way that this, whatever that wherever I had that nano lubricant, it wants this. So he wants those balls to be like these little. There's different things that these can do. So all right, so lubrication is a big field in polymers, but you can't get a degree in lubrication, tribology, they call it. So tribo, I guess means wear or something. And then, so there's like, if you go to the Air Force Research Lab, they have like 8 people, PhDs working in a tribology lab. Right, so it's kind of a big field. You can't get a PhD in it. Like there's no degree of tribology. Now, and it could be in mechanical, could be in polymer, it could be in chemical, could be in anything, right? So it's kind of like, it's kind of like this field that exists, but it's kind of lost. And they have their own journals and things, you know, like there's a journal where there's some, so it's kind of, there's a lot of these little niche fields, like we saw, like we looked at membranes. There's a whole field of membranes, right? But then you can't get a PhD in membranes, right? So somehow, and then there's a lot of these things. So anyway, anyway, so, and so like there are programs in this not in the US and not in Europe. So like there's programs in India and in Asia that are tribology kind of programs. So it's kind of weird. Like a lot of the papers are published from overseas, not from here, even though a lot of the jobs are here in this stuff. A lot of companies are interested in where, like the automotive industry, the oil industry, the biomedical industry. So they're all looking at the same stuff, but it's not like you'll see this in any course. So it's kind of good to look at this. Anyway, there's also a paper on, I'm not sure if I clicked it yet. So there's a paper on, he cites this paper, right? There's that thing on light scattering, Polymer character. So this characterization class has a lot of stuff on GPC. In other words, if you go to that, these are all different labs we did. And then one of them is like, one's DLS, and then there's a bunch of papers here on it. And then there's a GPC one here somewhere. So it's getting to be kind of old, but so the GPC lab is here. And then there's a bunch of things on GPC. There's GPC data. I mean, you could actually do the lab with the data that's here type thing, so. And then this bridge viscometer, I put that over in our thing too. So that's part of the GPC. Anyway, so that's a link there that you can look at if you want. And then that's the bridge viscometer paper. And then I think there's Mal's GPC. That link doesn't work. I don't know why, but you can go, that goes to the company that makes the GPC. This goes to the company that makes it, but you can find papers on Mal's GPC on this web page from this within this web page somewhere, but somehow the link I had is kind of deadish. I don't know. They put some kind of complicated linking code to it. What did I want to say? Bridge viscometer, Mal's GPC. Oh, lubrication regimes. This is a review paper that he cites. No, this is just a web page on lubrication regimes. Right. So you have, right. So if you ever driven a car or truck or something when you have these ribs in a dirt road, like the bumps, I don't know if you've ever done that. And if you go slow, it goes like lump, 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 right? And if you go faster, the faster you go, the smoother it gets, because you start to kind of hydroplane off the tops of the lumps. So friction's the same way. It's just like that. So initially, when you first start, it's very painful, right? Because you're just going up and down on these things. And if you get going like 60 miles an hour, it's as smooth as anything. But if you try to turn, you'll die, right? It's kind of like there's a risk factor to this. So anyway, friction's the same way. So it's going to be an initial regime where you have the grooves, the asperities, they call them, of the surface are locked together. So 70 to 80% of the wear in a friction situation happens when the thing isn't moving, just when it first starts to move. And then you're ripping the surface apart. And then after a while, it starts to like fill in the gaps. You're only ripping some of the surface. Then finally, you're like hydroplaning, like the lubrication gets in and it's just going smoothly. Right, so those are the three regimes. So he's talking about. So anyway, so this thing has that in it. There's a thing about this Hershey plot, and so this is kind of the. So in other words, these fields aren't that complicated, So he's got the three regimes. The first regime is the sticking thing with the asperities wearing out, and then the mixed lubrication, some asperity contact. So this is when you start getting going, where like it's still like, and the passengers in the car going, "Are you crazy?" And then you go, "No, just be quiet." Then you get to like 40. This is always a certain speed, and it'll just be like just smooth, So then if you slow down, then all of a sudden it's like all goes to heck. It's going to be like bumpy. Then finally it's like up and down again. So it's the same kind of thing. This is a coefficient of friction, the y-axis, which is So if you have like a drag force, the force it takes to keep going, like the frictional force, and then there's the force, the thing that's pushing the two surfaces together. So if you have no force pushing together, then that's easy to pull. But as you push harder, so you take the ratio of those two. That's called the coefficient of friction. Right. So you take the ratio of those two, that's this number. And the x-axis you would think would be the velocity, right? So it is kind of the velocity. It's the n is the velocity that you go on, or it could be the spin rate of it. If it's a shaft and an engine, so it's a journal bearing, they call it. So you have a hole, and then the thing goes in and it spins, right? So they call that a journal bearing, and then you'll see that throughout, like journal bearing. So you won't know what that is. So that's basically like an axle, right? So then ends, it could be the frequency of turning in the axle, or it could be like the speed or whatever, some kind of velocity. And then P is the force. P is the force that's pushing the things together. Force per length here, so that the units work out to a unitless number. So this is force per length, and that would be like speed per meters per second or something. And then everything works out then to be unitless. Anyway, so this is a unitless number that reflects kind of the speed and the viscosity, and that's the x-axis here, right? So so this is the 1800s, like this is a handmade plot, so, or 1902 or whatever it says. So there was some debate over who invented this thing, and the guy Hershey didn't exactly invent it, but it's called that. And the Strybeck, so Hershey number and the Strybeck curve are the two things, right? So I think that's as much as you need to know about tribology, right? Except that you could do this, you could make this your career, and there's plenty of money in it. That's kind of interesting, and all right. So then there's also so don't shy away from it. If you see a job, it's like tribology, lubrication regimes, and then I put nano lubricants. No, that's not it. There's a paper that I guess I didn't cite here that he cites. It's on, it goes through all the different kinds of lubricants. I guess maybe it's this. Is this a paper? No. I guess I didn't link that thing. Mols GPC, Polymer. It's probably there, but the link is broken. It's not written properly. Anyway, I'll put that up. But there's a thing that goes through. It's kind of interesting to read like all the different kinds of lubricants. And it's written by someone in Malaysia or something. Like it's not, like none of this stuff is written from anyone in the US, which is kind of weird, but because since this is a key element of industry, like every industrial company that's making things has a tribologist, at least maybe 5-10 tribologists, so, and no one's trained in it. It's basically, it's something you could get into, so anyway, so it's kind of worth looking at. Anyway, so what does this guy do? So this guy's looking at something flashier than just greasing a motor. He's trying to, that's how he got into nature. So he's talking about when people get arthritis in their knees, right? And then there's actually there's a web page for that too. The Sinovac, oops, that's what I wanted, the Sinovac thing. So Synovis, so this is a synthetic knee thing, right? And then there's they go through in here what you can do, so you can take like painkiller or stuff that prevents anti-inflammatory, and then you can go and you can do injections into the knee, right? So they're looking at the injection, and then you can have your knee hacked off and put in a fake knee. That's a common. Everyone's doing that now. I'd say like people over like 60, maybe a quarter of them, maybe more, have either a hip or a knee that's fake, So they go in, they actually chop and then drive a nail into the bone, like a spike into the bone. You've heard of this before, right? It's gruesome what they do. It's really, you can see videos of it online. It's totally gruesome. It's like carpentry on bone, They literally hack it open and they hacksaw off the thing and then drive a spike in, and then there's a ball and cup thing there. The cups usually hide in ultra high molecular weight polyethylene because the biggest problem there is that as you do that, so you'll get little abrasion particles come off, and each one of those little abrasion particles, the tissue will grow around it because the body's trying to protect you from little abrasion particles. And they'll eventually get to be like inflamed. Then they have to do the whole thing all over again with a new hacksaw, you know. So anyway, that's a failure. So ultra high molecular weight is the lowest abrasive material that exists. Like it's used for coal chutes, truck bed liners. Basically, if you want to have low abrasion, use this ultra high molecular weight. Same thing as milk jug, but the molecular weight is like 5 million grams per mole, you know. So I mean, the stuff's really interesting. Like you can also make a gel out of that and then spin it, and you can make bulletproof vest with it, with polyethylene, with a milk jug. You know, so it depends on the orientation of the chains, and somehow when the molecular weight gets high, it doesn't have these disparities that come up. So basically they use that in these joints because it's the best material. Anyway, so there's a huge business in these joints because a quarter of the people are going to end up with at least one and maybe four, like 2 hips and 2 knees. Right. So all the old people you see walking around, if they're walking, they got a piece of metal in this polyethylene cup, you know, and they're like, that gives them another 10 years, whatever. So then finally something else happens, you know. Anyway, but before you get to that point, and if you're afraid of having this gruesome thing done, they can just inject into the joint new lubricant. Like the problem is that the cartilage to the bone and the cartilage touches, you know, and the cartilage, I guess, wears away, or they don't know what happens, but somehow it becomes bone on bone, and that's when you get into a serious problem. So it needs more lubricant in there, like either to prevent the cartilage loss or to help with the bone on bone, I guess. So they inject into your knee, and that lasts this is something you have to keep doing. So maybe 6 months, go back in, get another inject into the knee. One problem is that the needle, so you don't want a big needle going into the knee, you want a small needle. So you don't want shear thinning fluid, right? So he shows that you don't want a shear thinning fluid here, because shear thinning fluid's going to do this business. He's got viscosity, shear rate. Shear thinning thins, right? So you get high viscosity here. That means you have to have a big needle to go in. And the actual, so these are synovial fluid. That's synovial, must mean knee or joint or something, right? So synovial fluid is a fluid in the joint and syn-visc is a synthetic uronic acid, which I don't even know what it is really, but something they stick into your knee that's kind of synthetic and kind of a bioorigin. Bovine synovial fluid, so that's a cow's knee, I guess, and then saline's the background. So saline's is a Newtonian fluid. It's flat, except for I don't know what this is, and I'm not sure what that is. And then his little 100 million grams per mole at 7%. So 3 million grams per mole. So Dalton is grams per mole and N is millions, right? So these are mega polymers or something. I mean, similar to molecular weight of the ultra high molecular weight polyethylene. That's the cup and the joint and cup thing. Anyway, so these things are high molecular weight because there's these dendritic structures. So they're actually pretty small. They're 50 nanometers or something in diameter balls, right? So, but they aren't huge. Ultra high molecular weight, if you stretched it out, would be like maybe 10 micron, pretty big, you know, 1/10 of it, maybe 1/5 of a human hair type diameter length, you know. So anyway, so then 23%, then one of the big ones, I guess, or the small one at 23% shows shear thinning. And he's saying that, well, low shear, if you want to inject it in a small needle, you don't want to have shear thinning because you'd have high viscosity, you'd need a big needle, right? So this is better. And also, if you look at the yellow is the bovine synovial fluid, and then some other osteoarthritic synovial fluid. So this is from someone that has arthritis. Their synovial fluid. I don't know why they take a sick person's synovial fluid. Maybe they have it. Like, who knows? Maybe some cadaver or something. Who knows? But anyway, so the red one has some shear thinning, and then the yellow, so there's some. But his stuff is flat, and the commercial Synvisc has this super. So his stuff's better than that because it doesn't shear thin. That's what he says. He's got his things are the yellow and the red here. Doesn't shear thin until you get to high concentration and low molecular weight. So And then he can show that they're spheres with an AFM. He sticks them on a surface and takes AFMs of it. Well, this is SEM, I guess, but he does AFM somewhere to get the, this is an AFM to get the, I don't know, to get the size of them or something, or get, from this, he can get the modulus of the little beads in water, you know. It's kind of interesting, you know, I guess it's surprising that it got into nature. And then he does, this is interesting too. It's a DSC, so it's thermal, thermal analysis on these beads, right? And then he sees where the water lets go, and it's got a, because the hydrogen bonding has an enthalpy, so he can measure it here. So it's I don't know, watts per gram. It's point, I don't know, 0.8 watts per gram. Seems like a lot. Like, I mean, so he heats it up. Somehow this is where the water comes off. Anyway, I'm not sure why it's at 0 degrees C, but so anyway, he can measure the amount of water by that depth of that peak, you know. So this is all in the supplemental, it's not in the paper. So he mentions the so anyway, there's that business, and then so that's kind of the game he's playing here. Let's see what else is in here. All right, so you, oh yeah, so the whole homework is about the analytic technique he uses. So he uses a GPC, which is also an SEC. So size exclusion chromatography, because the big things don't fit in, like it's diffusing and they can't fit into the holes. So their resonance times, and there's a gradient of flow going through slowly, but they're while they're flowing through, they're also diffusing to probe the gel. Gel has all different size holes in it. The big things can't fit into the holes, so they go with the current faster. And the small things spend a lot of time on vacation looking through all the holes, right? So they don't reach through until later. So it's excluding the size of the big ones. It's called size exclusion chromatography. Big things come up first, small things later. And it's called gel permeation chromatography because you have a gel and you're permeating through it at really high pressure, right? So anyway, so the whole thing's about a GPC that's got it's got a light scattering detector, so it calls it NALS, multi-angle light scattering. And it's the multi-angle light scattering give you race gyration, and it can also give you the concentration and the molecular weight from the zero intercept. And then that thing also has a dynamic light scattering detector on it where you can get the hydrodynamic radius. So he can get, I think he has a table here. So you can get molecular weight from the light scattering, from the zero angle light scattering. The zero angle intercept is zero concentration, like the Zim plot. So you're going to go to zero concentration, zero angle, and that's 1 over n is the intercept of some constant over the intensity. Constant times the concentration over the intensity gives you the molecular weight. And you get the weight average molecular weight, but since it's monodispersed in the GPC, that's the molecular weight in Dalton, which is grams per mole. So it's like 1,000,000 Daltons, right? And then is this thing, I've never seen this symbol before, but this is the polydispersity index, PDI. So this is MW over MN. I don't even know.
Yeah.
I had to just copy the symbol and put it into the homework because I can't even find that on a keyboard. I've never seen that before, but it might be something they use in biology or something. Then he's got his magic degree of branching number that I showed you he got from NMR somehow, even though it doesn't add up the way I saw it in any place. And if you Google degree of branching and you'll find out that everyone defines it their own way. It's like a free-for-all. So, and there's no reasoning behind the way they define it, you know. So anyway, nonetheless, that's what he's got. He might put it into some program and get that number. And it's always the same. So it's like, even when his numbers vary, it's the same number. So this size this is a hydrodynamic size. So he's down at the bottom, he says, right, let me see, I can see. Oh, he doesn't. Absolute molecular weight, omega confirmed by size exclusion, degree of branching, mega, intrinsic viscosity, and by quasi-elastic. All right, so he's got things. So viscometer detector and a quasi-elastic light. So this is all on his GPC. He's got kind of a fancy top line GPC to do this. right? So but he's got all the techniques we talked about in this one thing, so it's good. Anyway, so intrinsic, you can see the units are inverse concentration, so it's good. So it's not a viscosity. This is a C star, basically, for the stuff, 1 over C star. And then the size he's getting, that's a hydrodynamic size. But since the things are spheres, that's actually the radius of the sphere. It's probably better than any other size you could get, right? So, or since you're assuming they're spheres, and he says they're spheres, I guess you have to kind of believe him. There's polydispersity to them, but anyway, so that's kind of what's going on here. So you expect to see that the intrinsic viscosity is going to go with the molecular weight to the power either 0.5 for Gaussian, 0.8 for a good solvent, 2 if it's a rod, and 0 if it's a solid sphere. So he's got 0. 0 means it doesn't change, right? So that means he's got 3D objects that are water swollen ball bearings, I guess, for the friction thing. And these are his, so he calls mega once he gets above 1 million molecular weight, I think. And then this thing, so you got a power law slope here. So you can, he also compares it with polyethylene glycol, which is carbon-carbon, oxygen, carbon-carbon, oxygen. So that's like a same thing as polyethylene oxide, right? So that's a polymer that will grab onto water, just like his mega HPG. Well, and what HPG stands for. He defines it right at the beginning. HPG. Oh, is it hyperbranched? Definitely defines it someplace. Hyperbranched polyglycerols. Makes sense. All right, so so you can get the slope from this. So the way to get the slope on a log-log plot is like count how many decades. So you have so you say like if I'm going to do 1 decade here, then how many decades here, right? So the slope here is going to go up to that. So this is going to be anyway, I think it'll give you 0.8 if you do it right. Just like you can draw a line here and then draw a parallel line over here and see how many it goes here. In other words, if it goes 0.8 of the distance from there to there, not the numbers, but the distance between the decades. It's like it'll go to like kind of here from there. And I think that'll be the slope you have here. So it's a 0.8. It's a good solvent. So that makes sense. It asks you to do that. And then what else is he doing here? Then this is the conclusion. So it's like a 3-page paper, you know. This is the end of the thing. So this is his Strybeck plot, right? That's what it's called, right? He doesn't say here. This he does. So they're biologists. So they like to do. I guess they're biologists, or maybe rheologists do this too. But there's this whole statistical analysis of results to see relevancy that I don't know anything about it, and it doesn't make any sense. So, but there's a whole methods in biology to determine if things are true or not, right? So he's got this ANOVA as one of those methods. He says one way ANOVA, but the O in ANOVA is one way. She doesn't need to say one way ANOVA because ANOVA means one way. It's like something variable assessment or something or other. This is an acronym for some other thing that's commonly used in biology. Maybe you guys know what that is. I don't, but anyway, it's this statistical thing. You'll see things in here like a whisker plot. Like this is called a whisker plot. He says whiskers represent blah, blah, blah. I never heard that. So the references are all from biology in this thing, I think, because it's stuff I've never heard the terms used before. Then the Hershey numbers, is basically the velocity thing, right? And the coefficient of friction's the force thing. So those two would be plotted against each other in this plot to get the Strybeck plot for how the thing works. So you don't really see the different regimes in this. I'll put that other paper up that goes through the different kinds of lubricants, you know. He's got the the bovine serum and the synthetic. So he's trying to show that his things match up. Like his is blue and the other ones are red, pink and red. And he's saying that he can replace bovine synovial fluid with his blue things, the sub mega or whatever, or the 23%, I guess, will replace bovine. This Synvisc that people are injecting into their knees currently, he can replace with this HG3. And the advantage to his stuff is that it's not shear thinning, so he can use a much smaller needle and stick it into your knee. Whether you want to have nano balls in your knee is another question, you know, because Synvisc is just a lubricant. It's just like a long chain molecule. The balls, on the other hand, could stick around for a long time. And then you never know what nano is going to do to you. So maybe that it'll be fine, you know, but maybe, who knows. So there's that business. So I think that's kind of, he goes through a lot in the conclusions here. In summary, blah, blah, blah. And he talks about the different theories for in this last part. So that's the whole paper, is just this last part. It's just it's kind of like a letter. Nature communications are short, but they take a long time to write, and they're really difficult to get through an editorial. So you submit it, and the editor just says no. It doesn't give you any reason. If you're rich and powerful, then he'll send it out to review, and the reviewers will like haggle with you for 1.5 years about whatever, and it's supposed to be rapid publication of something. And then finally they'll publish it. I don't know, you have to pay to publish the stuff in it. So it's going to be like $500 on top of all the hassle we went through. But if you publish in Nature, like you start getting emails like invited talk, we'll fly you to Taiwan and like you can come and give a talk on this thing, and you know, so it's kind of worth the hassle if you have the time, you know. But generally it isn't worth it, you know, because it's just too much to go through for something that, like in this case, this really belong in Nature, and I don't see that it's any. It's just like it's almost like like something a company would publish, you know, like we developed this new thing. It's better than Sinovac, whatever the stuff is, Synvisc. That's like a company thing, you know. It isn't really science. And again, the guy, all this stuff about the HPG, he's already published since 2009. You know, the use in the knee. I mean, he doesn't actually do any biological tests here, so it's not medical, even though. And then you'll see like the list of people, right? So this is another thing, like a Nature paper, like look at all the people on it, because every one of them is going to get these invitations to go to like France or something to give a talk, you know. So basically, it's a lot of people, right? Not all of them could have contributed that much to this thing. They're from UBC, which is a good place. It's a good school. And then they're from Boston, Harvard. So see, this is where the money comes in. It's like, and then how you get something into University of Eastern Finland. I don't know, they're probably someone's friend, and then more Vancouver, more Boston stuff. Right. So it kind of shows you a little bit like how the world works too. Like, why does this thing get published? But it's nice because he's got this rump. So this is an anionic ring opening polymerization. So anionic gives you like monodisperse polymers because of living polymerization. So it doesn't have, usually there's a termination step in a polymerization. So there's initiation, propagation, termination. So anionic doesn't have termination. So if you start the stuff, so it's like a foot race and everyone has the same speed. They're all going to end up with the same length of chains if it has no termination. If it's got termination, then they kind of randomly terminate, and then you get a dispersion in the molecular weight. Right. So anionic is one of two ways you can get monodisperse polymerization, which means that this GPC curve should be just one. It shouldn't be like a broad peak with 1.2. It should be one. It should just be a spike. Like with an anionic polymerization, you should get a spike. But because he's got this game going on with the with all these different possibilities. That's where his broad peak comes from. And 1.2 is pretty narrow, but basically it's not anionic narrow. So that should be 1, you know, so because he's got all these different options as he grows the thing, and he needs these because this makes it into a water, like a water sponge. Like whenever he has hydroxyls inside, he's got a water sponge going. He kind of shows that in his picture, like he's got these internal hydroxyls that suck the water into the ball, make it swell out in water. Anyway, so what do we got here? Wheatstone bridge viscometer. So that the in the GPC, so you can just stick a capillary viscometer in it and then measure like the time of flow or something through it if you want, right? But that is a low accuracy apparently. So they've invented this. They invented this Wheatstone bridge approach, which is modeled after an electronic thing to measure resistance. It's in here. Bridge viscometer, yeah. So this is some company, but this seems to be like from NIST in DC. Somehow it seemed like it was in here. So he calls it SEC, is the same thing as GPC. Yeah, so it's just a different name for the same thing. Different if you're in biology, they call it SEC. If you're in polymers, they call it GPC. It's the same machine. There might be a little bit different column in it or something or other. And then low angle light scattering. And then if you want to get this intrinsic viscosity to get if you say you have a branch structure like this, then you get the light scattering will give you the molar mass of the thing, but you don't know the size exactly. You can get rates of gyration, but you only have the one number. So if you can get the hydrodynamic radius and the rates of gyration, you get the ratio, you can tell what the thing is. You can tell if it's a solid object or if it's like a linear chain, right? So the reason to have like this viscometer and the light scattering at the same time, and then do dynamic will give you the same, like the hydrodynamic radius. But anyway, he's got all three. So on this machine, so this is the Wheatstone. If you Google Wheatstone bridge, there's a wiki page. So it's got these two resistances, and this is usually an adjustable resistance. And then you have a voltage measurement across this. So it's electronic. And then this thing's unknown, R4. So you adjust this one until there's no voltage drop across that. And then there's an equation for what R4 is. It's going to be ratios of all three of these things. He gives it in here. So in the viscometer, I guess these are capillaries, the resistance, different kind of capillaries. Or they're a capillary flow, and then he's got the solvent going through one side and his solution going through the other side. And they rig that up somehow. So then he can change, then from the pressure across this, you can tell what the viscosity is over here. It's complicated. I don't fully understand it. It's in here though. This is the same equations that he uses. So this explains it a little bit better, right? You have the solvent viscosity and the viscosity you want, and somehow you do this. I don't remember. This is the equation he gives in the paper, and not in his paper, but in here. Like that's the same equation he gives someplace. RG. This is for the light scattering. No, here 4 delta P over P1 2 delta P. I don't remember where I had that, but basically that's the same equation. Right, so that's where that equation came from, if you want to know. I think it asks you to know. Wheatstone bridge, this is just asking you to kind of sketch, explain how GPC mols work. So multi-angle light scattering. This is not dynamic, right? So this is just GPC is a column, and then you have a high pressure pump. So how would you build? So you need a high pressure pump. It's going to have to go to like I think it's going to like 10 megapascal or 20 meg, so 200 atmospheres or something, pumping through. And the flow rate's really slow. So you have so the pump is the biggest part of the thing. The column's actually the biggest part. The pump is the second biggest. Then you have some tubes. You have a way to inject at a certain time because you're going to time the whole thing. So it has to be a discrete injection time. And then it's going to go through the gel column. So you have to have a high pressure tube filled with usually like polystyrene gel, basically napalm, and that's kind of flow through that. And then it's going to come out and you need a detector. And usually the detector is going to be an index or refraction because that's the cheapest thing. So you just have a prism and the light beam moves and you tell what the index is. And then you can add on all these other detectors, like his Mal's detector is just going to have a laser beam. You're going to have a cell with a flat window and a laser beam shooting through. Then you have like 3 detectors at angles, right? So you have collimated light coming in, monochromatic, and then you have to have these 3 angle things. And then from that, you can get the 0 angle. You can get the weight average molecular weight from the 0 intensity. It's going to go down, and then but it'll plateau out at low angle, and then from that low angle plateau you can get, from the way it tails over, you can get the rates of gyration. Right, so that's how would you convert the raw data. So the raw data from the GPC is going to be index or refraction, which you can correlate with the amount of material versus time. And then you need to correlate, so that you can do either a calculation, which you won't do, or you can run through standards to get like what molecular weight comes out at what time. So you get a conversion plot to convert time to molecular weight, and what it'll do is it'll flip it. In other words, it's a negative slope, I guess. So basically they aren't proportional, they're inversely proportional, or some functional. So you get that plot, and then you can convert the time data to molecular weight, and the index is basically the amount, and then you have the amount versus the molecular weight from that. That's the GPC thing. And then the mols, what raw data, how do you convert the raw data? I'm trying to get you into the mood of like how you, when someone asks you, what is this thing? This is the answers, the questions you should ask yourself. How do I build it? What does it spit out? How do you convert what it spits out to what I need? If you know those 3 things, then you have a rough idea of how it can mess up and what you can trust and what you can't trust. Like it's not given the right answer. Why is it? Well, you go back and you say the components of it, which one broke. You can say, is the conversion program working, or does it have limits? Right. And then you can say, like, let's look at the raw data. Does it look like the way it's supposed to look? So you can kind of figure out what the problem is if you look at the machine in those contexts. Then how do you convert what moment of molecular weight? So moles gives a weight average molecular weight, but it doesn't matter because it's monodispersed. So all the moments of molecular weight are the same for the fractions that are coming out of a GPC. Then table 1, degree of branching, size, intrinsic. This is his equation for degree of branching. So does that seem reasonable? I think no, but you could say yes. I mean, basically N groups, I don't see what N groups have to do with branching. That's one of my main problems here. Like what, if you're, I mean, the bigger it gets, the more N groups it's going to have because it's branching out. So that's weighting towards more branching naturally, right? So that function doesn't seem right to me, but the size, someplace he gives that equation, but it doesn't add up in his table in that other paper. So anyway, and there's other equations people use that, which are equally not understandable. So I'm not sure there's an answer to what the right way to do it is. This size, so he gives the size, which is he just calls it size, but it's a hydrodynamic size because he uses quasi-elastic light scattering on the mol. So he takes one of those angles, and then he looks at the light flicker from it, and he feeds that into a correlator. So it says the same thing, like explain how that hydrodynamic. So how would you build it? So you have to have a light detector that's going to be able to, a Fuller multiplier tube that has a fast response time. You already have the laser and the beam coming off. So you're going to get the intensity as a function of time, and then you need a computer board that's a correlator that no one understands what it is. It's just a black box. And that signal is going to feed, I mean, the guy that built it knows what it is, and it seems to work, but basically don't know how it works. And that's going to convert the noise signal into a correlation function. Will be an exponential decay. You're going to fit that with a single exponential or multiple if you want. And that's going to give you relaxation time, or this gamma, capital gamma. And gamma is 1 over the correlation times. That's going to be like the diffusion coefficient. So the square root of 2 times the diffusion coefficient times something. There's a diffusion coefficient times a, let's see, the time, diffusion coefficient times the time gives you, what's the equation? 2 diffusion coefficient time gives you what, this, something, Q? Okay, oh yeah, Q squared, the size. Yeah, Q squared is the size, thanks. All right, so you have Q squared because it's diffusion. Anyway, it will all work out for you, I think. So that's the conversion part of it. You get the noise pattern. The correlator gives you the, so that's part of the instruments, get the noise pattern and convert that to a decay function, and then you fit that to get the tau. So you can see the problem's going to be in the fitting. Like is it really a single exponential? Is it multi-exponential? Is it smeared out? Like, can you really fit it? Or is it ballistic motion, which would just be a straight line? It could be like if there's a charge in it or something, like the things fly across, then you won't get this exponential decay, you'll get something else. You know, so there's ways to kind of analyze what's going on if you think about it. And how do you convert? So you fit it and then get the diffusion coefficient KT over 6 pi viscosity times the RH. Diffusion coefficient gives you directly RH. And so, and then intrinsic, the Wheatstone bridge things is that paper, and then explain the following statement. Okay, so the size does not scale with molecular weight as with linear polymers and low molecular weight. That's figure 2A is supplemental. It's got all this weird data to start with. There's figure 1, figure 2. It's figure 3. Figure 2A is a supplemental from this guy. I think. 1, S1, no. What is the question? Oh, from the figure 2A supplementary table 1. Oh, figure 2A from the main paper. Shoot, all right, sorry. Figure 1, figure 2A. Okay, yeah. Yes, the size and molecular weight goes up. His things don't do that. Size that lies between linear polymer and dendrimer data further indicates that mega more compact than linear polymers. So just asking you to comment on this. Offering interior room between branch units. It's got kind of flowery wording, you know, interior rooms. I mean, it's nice. It does that. That probably helps with the nature thing. Mega intrinsic viscosity compared to other intrinsic viscosity. Mega does not change molecular weight. That means it's dense. I mean, so if this doesn't change, that means that the A coefficient, that the C star is fixed. In other words, it doesn't have it's a solid object, right? So then give the Einstein equation. So that's 1 plus 2.5 times the concentration gives you the ratio of the viscosities. And so it's basically the intrinsic viscosity equation, but with 2.5. And then the displacement law, I went through that in class, right? And then expected values for Gaussian chain, that's a 0.5, 0.8, and 2. Why you get this bell-shaped curve in molecular weight. So I'm not sure there's an answer to that. It's got, well, you can try to explain that. And then the slope of the blue circles is 0.8, so it's expanded coil. Count the number of decades, tells you how to do it. What type of structure does correspond to expanded coil? And then the Strybeck plots. That's just comparing those things. We did that already. Yeah. Shows low molecular weight, displays shear thinning. So this is just the shear thinning thing. He talks about this in the paper. So hopefully it's not too bad. I mean, it's a 3-page paper. How bad could it be? But hopefully it gives you some idea. I'll try to get that. His reference to the viscosity, I have that, and it's in there, but it isn't showing up. So I'll put that up too. You know, it's kind of interesting to read about the different kind of fluids for lubrication. I think it's at some point you'll run into it, I guess. Although I've never really done anything in lubrication, but if you work in an industry, like I think you'll find it. Just everyone needs it, so. Anyway, that's about it. Any questions or anything? Yeah. So we're going on that tour. I want to leave like 11:30. I'm gonna go eat a peanut butter sandwich first. So you want to meet me down in my office in like
Yeah.
20 minutes or something?
Oh.
492 Rhodes.
Yeah.
Yeah,
Now, Crystal,
you're coming too, right? Yeah,
come
yeah, you two and oh, we have 4 people, huh? All right,
on there.
okay. You're going or
Yeah.
are you driving?
I'm driving myself, yeah.
Oh, are you coming back?
So I'm not directly.
Yanchi's coming back. Can you give one of them a ride there though?
I can give one right there.
Okay. Because I only got room for 3, I think, but yeah, Yanchi can give you a ride back. He's got a bigger car. Yeah,
I'm going to Dayton.
okay. Anyone want to go to Dayton?
Yeah, no.
Hot time in Dayton tonight. All right, I'm gonna eat my peanut butter sandwich. So who's gonna go? Oh, what's your? Oh, Noah, yeah, okay. You're gonna go with Noah or is that? And then back, Yanchi said he can give everyone a ride back. He's got a bigger car. Because I live out there. I live right near that area, so I'm just gonna stay there. Guess I have to meet someone out there.